Okay, let's start. Hello, everyone. Welcome to our virtual webinar series by IFCC. Today, this webinar will follow a funnel approach, moving from general concepts to specific applications. We will begin by exploring the fundamental concepts of biosensors and artificial intelligence, as well as their integration. Following this foundational discussion, two final two, the final two speakers will discuss specific examples, demonstrating how biosensors and artificial intelligence are applied in practice. This structured approach is designed to provide you with both a broad understanding and practical insights into these cutting-edge technologies. Also, you can ask your questions by attendee question sections on the left side of the screen. And end of the webinars, our speakers will answer them. Now, our first speakers, Dr. Deniz İlhan Topçu, is a medical doctor and laboratory medicine specialist dedicated to bringing clinical practice and technological advancements. Eager to harness the power of data-driven tools in diagnostic, he pursued a degree in computer engineering, followed by a PhD in biochemistry. His doctoral research focused on applying AI to the auto-verification of clinical laboratory results. And also an expert in R programming, Dr. Topçu has developed that data analytics solutions for clinical laboratory management and actively conducts research on data analytics and machine learning in medical diagnostics. His expertise is further highlighted by his consulting role for the EFLM working group on biological variation. Now, screen is yours, dear Dr. Deniz İlhan Topçu.
Thank you, Osan, for this nice introduction. I'm sharing my screen. Okay. Good morning, good afternoon, good evening, everyone, and welcome to my presentation on artificial intelligence approaches in point-of-care biosensors. My name is Deniz İlhan Topçu, and I am honored to have you here today. I have no conflicts of interest or financial disclosures related to this presentation. Today, we are going to learn the basics of biosensors and AI, including key concepts and uses. We are going to understand how AI and ML optimize biosensor data processing, and finally, recognize the challenges and opportunities of AI in point-of-care biosensors. As healthcare evolves, the integration of advanced technologies like AI into diagnostic tools is becoming increasingly critical. Together, we will explore how these innovations are transforming point-of-care testing, driving efficiency, and opening doors to personalized medicine. To this end, my talk scope is here. First, we are going to talk about biosensors. Then I am going to give some basic information about AI. Then I am going to give some examples of these both different fields. So let's start with point-of-care testing and biosensors. From ISO definition, point-of-care testing is testing that is performed near or at the site of patient. Also, it provides a more detailed explanation. Point-of-care is a method of clinical laboratory testing in which the analysis is performed at the site close to where healthcare is provided to the patient. So the main idea is here giving results more quickly to the patients, so we can achieve immediate of response and effect on medical decision making. As you can see here, the first testing, Sumerian and Babylonian physicians of 4000 BC recorded their assessment of urine on clay tablets. Ancient Sumer, one of the earliest civilizations, recognized that urine characteristics were altered with different disease. And around 1970s and 80s, we started to talk about biosensors, and now we are talking about intelligent biosensors, which is integration of AI ML tools into biosensors. First of all, I want to give this information because it is very important. Point of care test is not only about making tests at home or onward. It can be applied everywhere. For example, primary care, secondary care, including, for example, helicopters. So it is very important to have accurate results with point of care testing. Point of care testing uses different approaches, actually two different approaches, chemosensors and biosensors. And today's talk about biosensors, which provides more detailed and uh, accurate results about point of care testing. So what is biosensors? It is analytical tools that identify and measure target analytes by combining components of biological recognition with electrochemistry. One of the most significant areas is biosensors, which have evolved from conventional electrochemical biosensors to implementable and wearable biosensors. And the second talk will be discuss these tools, for example, continuous glucose monitoring. The glucose meter is a fundamental example of a biosensor. It uses glucose oxidase as the biological recognition element to specifically interact with glucose in the blood. The resulting chemical reaction generates an electrochemical signal that is captured by a transducer and processed into glucose concentration reading displayed on the meter. Leland C. Clark Jr., often referred to as the father of biosensors, made pioneering innovations that laid the foundation for modern biosensor technology. To better understand the role of AI in biosensors, it is essential to first grasp the fundamental components of biosensors. These are analytes, recognition elements, transducers, and data handling elements. Starting with analytes like ions or proteins, they interact with recognition elements such as antibodies or enzymes or aptamers. These interactions then generate signals, which is processed by transducers. Then they convert them into measurable outputs using electrochemical, optical, or electrical methods. And these outputs handled by data processing units to produce reliable diagnostic results. So what is an analyte? It is any biological marker targeted by a biosensor. They can be ions, nucleic acids, proteins, viruses, or human cells. They should link to a biosensor application. For example, disease-specific biomarkers. They must be in sufficient concentration in the target biological fluid. They should correlate with health parameters, and they known and selective recognition elements should be available for recognizing these analytes. And this is maybe the most important part, because the analytical specificity is related with recognition elements itself. So these recognition elements can be biologically derived or they can be synthetics. Because of these synthetic versions today, these biosensors also called biomedical sensors. The recognition elements can catalyze some reactions such as enzymes, or they can interact with molecules, affinity-based recognition elements. They bind specific to the analytes such as immunoglobulins. Their nature can be protein-based, nucleic acid-based, or they can be completely synthetic. This is all about analytes specificity. Then after this interaction with recognition element and analyte, these transducers convert molecular interactions into measurable signals for analysis. Key to enabling biosensor functionality and interpretation comes with these transducers. Common transduction methods are electrochemical, electronic, colorimetric, and optical methods. But there are also less common methods such as acoustic, thermal, and piezoelectric versions. As you can see here, actually, it is very easy. The current increases with increasing glucose concentration due to the hydrogen peroxide released, and consequently more electrical signals are transferred to the electrode So with transducers, we detect this current, and with the last part, data handling part, we can convert this current information into glucose concentration. And data handling actually involves three parts in itself: data acquisition, analysis, and interpretation. These details are important because I am going to show some AI ML tools which improves these all steps. Data handling can be very simple, like only visual determination such as pregnancy testing, but also can incorporate more advanced systems. For example, they can modify data, correlate data, or they also filter some noise to obtain more accurate results. When we look at the advantage of biosensors in POCT, they provide on-site screening, which enables immediate diagnostic at patient's location. They use reduced sample volume. They are generally can be cost effective if used correctly, and they eliminate the need for trained laboratory personnel, so they are user friendly. But there are some hurdles related with POC biosensors. Their sensitivity of transducers can be low because they can be some high background noise. Their detection capabilities can be limited. For example, single target detection can result in less accurate outcomes, and environmental variability is also important because you cannot control all the settings such as temperature, humidity, or the lighting. All these concepts affects the accurate results. But luckily, with some AI applications, we can overcome these challenges. So I want to give some information about artificial intelligence at that part. Then I am going to talk about integration. This image captures a defining moment in history of AI. It highlights the Dartmouth Summer Research Project, held in 1956, where the term artificial intelligence was coined by pioneers like John McCarthy. This event laid the foundation of AI as a research discipline at that time, with the core idea that intelligence could be described and simulated by machines. The pivotal moment continues to influence advancements in AI today, as you know, because now we are talking about machine learning with more complicated configuration. We are talking about deep learning, and now the generative AI is real game changer because it's brought AI applications to all people use. But how AI ML works? Let's briefly explore this concept. It starts with data, historic data. These tools, AI and machine learning tools, detect patterns, relationships, which can be very difficult for humans, and they capture this information as a model. Then new data enters this model, and then we obtain insight about new data. This is the basic principle of AI ML tools, how they work. Also, we should classify machine learning because there are different algorithms and approaches. For example, the main three aspect is supervised, unsupervised, and reinforcement learning. And also these days, semi-supervised learning is also becoming important. But generally, as similar with other healthcare setting, point-of-care biosensors generally leverage supervised learning algorithms. Also, some clustering methods are important for example, molecular discovery. These are unsupervised learning tools, and there are some reinforcement learning applications related to biosensors. And these algorithms, neural networks, linear regression, decision trees, random forests, there are many different algorithms can be used for supervised or unsupervised setting generally. This diagram represents the basic workflow for machine learning model development and evaluation. The process begins by splitting a data set into subsets for development and validation. The training set is used to build the model, while the tuning set helps optimize its parameters. Internal validation ensures performance on unseen data during development. Finally, if possible, external validations test the model on entirely separate dataset to evaluate its generalizability and real-world application. This workflow is crucial for creating reliable and robust machine learning models. So let's get back to point of care biosensors and their AI integration. AI ML applications are often thought of as a being solely for data analysis. However, AI ML contributes to all stages of biosensor development, as I just mentioned, from analyze to recognition elements, transducers, and data handling. That said, our focus today will be on the data analysis aspect. This slide highlights the role of AI in elite selection, which is a critical step in biosensor development. AI can analyze large data sets, for example, biological data sets, omic data, proteomics, genomics, etc., to find biomarker related to disease. AI can also identify biomarkers that correlate with disease using AI models, such as classification, clustering algorithms can be used for these purposes. AI tools also enables the detection of patterns with biochemical data, allowing the identification of multiple biomarker signatures, which can enhance diagnostic accuracy at the point of care. AI also improves the recognition element selection. This can be classified as top-down discovery or bottom-up discovery. In the top-down discovery, AI can be used for analyzing large data sets, which is very complicated if you do it manually, and it discovers some novel recognition elements. Or it can be used as a bottom-up discovery tool, such as AlphaFold. Molecular modeling via AI tools predicts and designs new recognition models. Maybe the most important example about this bottom-top approach is AlphaFold, which can predict proteins' final 3D structure using the amino acid sequence and other related data. AI also helps material design, biorecognition-free transduction, instrument miniaturization for transduction step. Finally, AI in data handling can help all data acquisition, data analysis, and interpretation part. For example, for data acquisition, neural network-based adaptive filtering techniques can help to reduce noise, because it can filter background noise efficiently. So we have higher signal to noise ratios, and it affects our detection limits and accuracy. So with these filtering techniques, we can have increased detection limits and accuracy. Or at the data analysis part, these AI tools can also process multiple biomarker signals, and now we can have more comprehensive diagnostic information. Multiplex analysis is critical advancement in diagnostic. This figure illustrates an innovative approach to cancer diagnostic using carbon nanoparticles. In essence, it uses some neural network models to classify a stage of data handling, so it really improves the patient outcome. Also, interpretation is important step. For example, with real-time application of AI tools using continuous glucose monitor biosensors, these real-time monitoring glucose levels can be used for prediction of hypoglycemia. So patients, they improve patient outcome because they prevent hypoglycemia, because they critically warn the patient there will be hypoglycemia. So this real-time monitoring is also important. Other example, another application, computer vision. Algorithms can calibrate the dipstick photo. So as I mentioned before, environment settings cannot be controlled for POC testing, but with computer vision, this tool can accurately quantify the albumin creatine ratio, and patients can easily monitor their their albumin creatine ratio in urine at their home setting. Also, if we want to talk about little about workflow for machine learning development, it is very similar with the previous mentioned model. First, we have some. We should identify the problem. We obtain data. We then apply a model, and after obtaining the model, we train this model. After training the model, we see if there is enough performance for this model, and if the performance isn't in our expectations, we can remodel these tools and optimize one more time after obtaining related information. But again, with similar with healthcare setting, AI ML applications have also some challenges related to biosensing. For example, lack of quality data is always problem, similar with healthcare. Also, biased screening data can cause problems. There can be hardware limitations, and accessing open access analysis programs or data can be problematic. But at the end of the day, this sensor will be our feature. For example, combining AI and microfluidics of autonomous on-chip diagnostics will reduce manual intervention, so we will have intelligent microfluidic devices. And integration with telemedicine, real-time data transmission from POCT devices to healthcare providers enable remote monitoring more efficiently. Also, enhanced multiplacing capabilities will increase patient outcome easily. And all these results actually yields into personalized medicine, which is very hot topic today. As a conclusion, continued advancement in AI ML tools and biosensor technology will lead to the way for improved diagnostics. AI integration enhances the efficiency, accuracy, and accessibility of point-of-care diagnostics. Interdisciplinary collaboration to bridge gaps between AI, engineering, and clinical applications is important. Thank you for your patience, and I am welcome your questions and comments.
Thank you, dear Dr. Deniz İlhan Topçu, and thank you for time considerations. Okay, now let's start our second speaker, Dr. Ebru Saatçi. She was graduated from 9 Eylül University Medical Faculty, Izmir, Turkey. She got her PhD degree in biochemistry from Middle East Technical University, Turkey. She has a member position on the Committee on Mobile Health and Bioengineering in Laboratory Medicine for the term of office 2024 and 2026. And she is a member of the Turkish Journal of Biochemistry editorial board. She has recently been working on electrochemical biosensors design and development. Okay. Now, screen is yours, dear Dr. Ebru Saatçi.
Thank you. I'm going to share my presentation. And let me share it. Okay. Hi to everyone in different time zones. I am happy to participate in this webinar series with my colleagues from Turkey. Today, I will discuss about CGM electrochemical biosensors and their integration with artificial intelligence. I will start with intelligent biosensor properties. The slide here shows the effectiveness of intelligent biosensor in analyzing complex and raw sensing data from a signal. When we categorize a signal coming from a sensor, the algorithms can sort the sensing signals based on the target analyte. And as we know, biosensors are affected by sample matrix and operating conditions. When used on site, they can significantly interfere with contamination. On this hand, ML can check the signal anomalies and correct sensor performance variations. When we come to noise reduction, the sensing signals always include the noise coming from the sensor's electrical subunits. Therefore, it is possible to train ML models to distinguish the signal from the noise. Moreover, proper deployment of ML methods can discover hidden relations between sample parameters, sensing signals through visualization, and mine interrelations between signals and bioevents. And also, ML can assist biosensor readout directly, automatically, and accurately, and rapidly, which is important for on-site detection and diagnosis. It also gives us more sensitive and specific results. After covering an intelligent biosensor, I would like to continue with an intelligent biosensor development example, CGM, intelligent biosensors. And an electrochemical glucose biosensor consists of working electrodes, reference, counter electrode, and an electrolyte solution. This is a classical diagram of an electrochemical glucose biosensor. In the circuit, the working electrode facilitates the electrochemical reaction with the target analyte, and while the reference electrode maintains a stable potential for accurate measurements, and the counter electrode completes the circuit and allows charge flow. And the electrolyte facilitates ion flow between electrodes, generally between counter electrode and the working electrode, and the sensing mechanism, including enzyme, involves redox reactions, wherein the target analyte undergoes oxidation or reduction at the working electrode surface. Go through the evolution of different generations of electrochemical glucose biosensors. We should start with the first generation. And in the first generation, the catalyzation of glucose oxidation through glucose oxidase, producing gluconic acid and hydrogen peroxide, and from the glucose. This gives us an electron current, and we can detect the electrochemical signal from the biosensor. This is the first generation. And for the second generation, it employs a non-physiological oxygen-free redox medium for electron transfer, again, from glucose oxidase to the sensing electrode surface. And for the third generation, enable direct electron transfer by reducing the distance between the enzyme and the electrode through the enzyme immobilization on the surface of the electrode. This is the third generation. And on the other hand, we have another type of biosensor, which includes glucose dehydrogenase as an enzyme. And in here, the function, it's a lower detection potential we have, and are unaffected by the presence of oxygen in the sample. This gives us a more stabilized conditions. And the last one, for the fourth generation, we have a modified non-enzymatic electrodes with nanomaterials. This can perform enzyme-like reactions to transfer electrons again, especially under the extreme conditions. We can have nanozymes. If you can hear that, if you already hear these nanozymes, you can understand the probability of the usage of these nanozymes instead of the enzyme. And figure outlines the evolution of biosensors for wearable CGM applications. The period starts with oxygen detection by an electrochemical biosensor. The field saw a significant breakthrough in 1962 with an introduction of glucose oxidase enzyme-based biosensors by Clark and Lyons. This biosensor facilitated the monitoring of glucose levels through enzymatic reactions, leading to development of first-generation glucose sensors. Afterwards, throughout the mid-20th century, Clark and Kadish significantly contributed to biosensor technology by developing the first glucose meter in 1970s. After that, we can see the third generation, like immunosensors and some glucose meters with optical sensors. And on the other hand, we will come to fourth generation. In 1987, Wilson's needle-type glucose sensors revolutionized glucose sensing technology, improving precision, selectivity, and patient comfort. This is the first glucose test strip, actually, as a fourth generation. After that, the first commercial CGM was developed in 2000 with GlucoWatch. And for the fifth generation, we can see wearable biosensors, CGMs, and I'm going to talk about some glucose monitoring methods, depends on these wearable biosensor methods. And here I would like to give some glucose monitoring examples according to their sample type. And all samples have their own method. For example, for the blood, a self-monitoring blood glucose technology, it's a self-monitoring blood glucose technology throughout electrochemical fingertip blood sampling. And B is for interstitial fluid detection, glucose detection. And it's a CGM, it's minimally invasive implantation and electrochemical sensing probe again. C is for saliva. It's a non-invasive CGM based on saliva with a telemeter on teeth. And this is an electrochemical integrated device for non-invasive CGM based on sweat. And for tear, we have a minimally invasive electrochemical CGM based technology. I will tell a little bit more detailed in this one. And this last one is for urine. It's an invasive CGM biosensor based on urine with Fourier spectroscopy detection. This figures gives us non-invasive glucose monitoring device examples. For example, in A stretchable Sweat system for glucose and lactate colorimetric monitoring. It's a colorimetric monitoring with an electrochemical measurement. Both of them are used in this biosensor development. And here it's an in vivo salary glucose monitoring with telemeter again on teeth. Here it shows a bioimpedance spectroscopy based device that could be implanted in the body for glucose level monitoring. And D is a transdermal device for glucose monitoring based on interstitial fluid with level detection, glucose level detection in exhaled breath. And is a transdermal device for glucose monitoring based ISF extraction with the differential structure to remove passive sweat effect with electrochemical measurement. This is a colorimetric microneedle patch for sensing glucose, lactate, cholesterol, and pH levels in ISF. And the electrochemical, again, wearable biosensor based on microneedles for the detection of glucose, lactate in ISF. The final one is an interesting one. It's a Novio-Sense electrochemical glucose sensor. It's formed behind inferior conjunctival fornix, continually measures basal tear fluid glucose levels. This is an overview of FDA-approved glucose monitoring devices. The first one is the Dexcom G6, and it provides real-time glucose readings every 5 minutes. The second one, AcuCheck Guide, it provides easy-to-use features like spill-resistant vial. It measures the blood glucose level. It's actually blood glucose meter. The first one was the CGM, and the third one touch Vario Flex. It's again offers blood glucose readings. May include features like wireless data sync with compatible applications. This is about Freestyle Libre, measures intestinal fluid glucose levels. Users can also use sensor with a reader or smartphone applications. This one is a hybrid one, Medtronic Minimed. It is with insulin pump system, and that automatically adjusts basal insulin delivery based on CGM readings. And the final one, Medtronic Guardian, it's a CGM, provides real-time glucose data with an insulin pump. This one is the latest one, which is approved in 2024 from get its approval from FDA. Dexcom Stelo glucose biosensor system. It's a state-of-art glucose biosensor system designed to provide continuous and real-time monitoring of blood glucose level in intestinal fluid. And the system includes a small discrete sensor applied to the skin. The sensor continuously measures glucose and sends to the data receiver or smartphone applications every 5 minutes. From now on, I will continue with AI integration with CGMs. In AI sensor network, connected information in CGM is transformed into AI data process via signal conversion, and they will generate a decision layer. The adaptability of big data processing in clouds provides a sense of reassurance in the efficiency of AI integrated biosensors, and AI-BN application of AI biosensor networks could be wearable, implantable, embedded, and ambient AI biosensor networks. The interface can provide a user with information via wireless data connection between AI biosensors and smartphone-based platforms or other intelligent devices. The most popular AI algorithms applied in diabetes care are support vector machines, artificial neural network, and supervised machine learnings. Artificial neural network-based analytical techniques follow a pathway from patients with the biosensor and going on exhibit biomarkers for disease, continuous real-time connection, time data collection, abundant raw data collected, train models, data preprocessing, applying ML and ANN techniques, and finally reach to output automated continuous prognosis. The combination of machine learning and CGM has shown its promise in different application scenarios for diabetes management, such as calibration, decision support systems, closed-loop control, patient self-management, and automated screening. As we know, during pandemic conditions, we understood the importance of smart healthcare technologies. The need of AI integrated intelligent biosensor to reach a relevant doctor in a variable hospital became apparent. So due to these necessities, smart healthcare utilizes many information technologies such as the Internet of Things, cloud computing, big data, and artificial intelligence to increase its efficiency and make it more user-friendly. And we need a smart tech healthcare solution to detect diabetes in rural areas or remote locations, as instant medical facilities are not available there. This is the pathway, like a pathway, the signal coming through the glucose glutathione monitoring and goes through the storage of glucose values in cloud to the hospital, nearest hospital for the treatment. Then the doctor and technologist got the results, and response will be again follow this path to the patient. The result, smart technologies will become a part of our lives. Thank you for your kind attention.
Thank you, dear Dr. Ebru, for deep insights about the subject. Now, our last and third speaker, Dr. Zihni Onur Uygun, received his PhD degree in Ege University in the area of medical biochemistry. After PhD, he pursued postdoc education on translational medicine in Koç University 2022 in Turkey, and chemistry and molecular science in Clarkson University 2023 in USA. He has been working for now Kafkas University Faculty of Medicine as associated professor since 2022. His major subjects are biosensors, bioelectronics, electrochemistry, single entity electrochemistry, lateral flow biosensors, and their medical applications. For 2 years, he has been working on the integration of the decision mechanism provided by AI and ML for medical biosensors applications. Okay, you can start your presentation, dear Dr. Uygun.
Hello everyone again. The journey for the biosensor technology and specific examples by starting to cancer or virus based version of the AI based systems with the simple glucometers. So see a glucometer. So this creates a biochemical reaction in our body. Glucose in the blood.
Sorry, Doctor
Another.
Onur, I have to interrupt your presentation. There is a problem about your voice. Can you start again?
Okay.
Can you check your voice system, microphone or so?
Can you hear me?
Yes, we can hear you, but problematic. I think your connection is has problem.
Do you? Is it okay?
No, no, sorry. Dear Smeralda, can you help us? No, no, your voice is
Can you hear
problematic.
me right now?
No, no, we cannot hear
Share.
you suitable properly.
So, and I can hear you also.
Dear Dr. Onur,
Yeah,
I think
can you log out and log in again just to try if something?
yes.
Yeah, okay.
Okay, now let's wait for Dr. Onur. I think his internet connection has problem.
Can you hear me right now?
Yeah, the Dr. Onur. Now, excellent.
Okay.
Okay, let's start the beginning of the speech.
Okay. Sorry for the problem, and the journey continues with me with the learning machine for the biosensor technologies. Then I will give you very specific examples and the integration of the AI and machine learning and deep learning, just as mentioned by my colleagues before. And let me give you an example. What is a smart biosensor? So this is just like a biosensor, as you can see in this picture. So this is just like a simple glucometer. It has ability to replicate glucose conversion of the glucose in our blood into secondary molecules. And it can only count by electrons which released by the biochemical reaction. So this device can just give you the concentration by combining the electrons in time. So we programmed this device by using the calibration curve of the glucose by combining the releasing electrons. So then it becomes the smart biosensor. The smart biosensor can discriminate just the glucose instead of other molecules. When you use an iodine-based antiseptic on your finger, or if you have a high vitamin C concentration in your blood, so this device will give you higher glucose concentration. And this biosensor technology cannot discriminate you are a diabetics or you are using a different chemicals, and it cannot discriminate in what is in your blood. It can just count the electrons in your blood. When it has become the smart biosensor can analyze and decision-made systems. They are autonomous systems. So they are continuously detect anything, and you can access remotely from this anywhere from these devices, and they can analyze multiple substances simultaneously, and it can decide. So the last one is evolving. They can really learn by detecting new samples, and this device can learn and learn and learn, so they can evolve themselves to smart biosensor technology. So let me give you a couple of AI-based information, so we can continue very specific examples that we developed in our laboratory. So the basics of AI starts with the basic algorithm. So basic algorithm can say if and then. What is if? For example, if your blood glucose level is higher than 120 milligrams per deciliter, then the system will give you an alert. Your blood glucose is high. Or if you have a good cancer biomarker in your blood, so the system will say your cancer biomarker is high, but it will not give you anything about your cancer, your situation, or another thing. It will just analyze the patterns, and it will give you a triggered alert. So the machine learning we can use machine learning in detection of the biosensor technology, identifying some patterns. Just as I mentioned before in my second slide, so that glucose biosensor cannot discriminate an iodine-based antiseptic that used in your to clean your finger, or it cannot discriminate your vitamin C concentration in your blood. But the machine learning thing can isolate only the glucose signal, and it can discriminate it can detect only glucose signal and give you the main the concentration of the glucose. It is very useful machine learning thing for the biosensor technology, and they have ability to improve and optimize its codes in time, and it will give you a very very powerful and very precise results. So another one, intelligent-based, AI-based basic is deep learning techniques. Deep learning techniques are very useful, for example, lateral flow-based system. The lateral flows are that we are using as a pregnancy test or COVID or fast COVID test. So the LFA-based strips can be analyzed by conventional neural networks. So we can only see in the pregnancy test or the COVID test, you are COVID or not, or you are pregnant or not, but it will not give you anything to concentration to the target molecule or target something. Or the Professor Sachi talked about the continuous glucose biosensors. So recurrent neural networks are very good for effective time series and the data like tracking of the biosensor reading. And the AI. So what we are doing in our lab, we are forming our small codes, small machine learning codes to analyze our outputs. So this outputs integration in time, and we are putting some specific data, and all the specific data and all the machine learning, all the deep learning techniques integration into to form an artificial intelligence. So if an artificial intelligence, for example, a glucose biosensor or a DNA-based biosensor or lateral flow-based biosensor, it can really decide. It can decide you are cancer, you are diabetics, and you are in a very hard situation to see a doctor. So these are the basic things, and my colleagues already explained the AI. And let me take you to my lab in my kitchen to show the some specific examples. So the machine learning point of care sperm testing. Me and my colleagues from Koç University, we have been developing a sperm-based sperm testing technique. So it can detect, it can count the number of sperms, pH, and the fructose molecules and the sucrose molecules inside of the sperm test. Sperm is a very different sample because its viscosity is very different by comparing the blood or the urine. So how we do that? Let me tell you. Think about a baby. You are teaching a baby to look into a picture and to analyze it. So we use navigators. Maybe you can see in the Aruco markers in this picture A. These Aruco markers can say to navigate the picture, and says the program just analyze between those Aruco markers. So those between those Aruco markers, we have scales and we have different colors. So first of all, we isolated the specific colors on this flower-shaped lateral flow technique. So maybe you can see on the right top corner in the B, there are different color intensities of the tests. Maybe if we can look at these tests, we can say it is positive or negative, but the system, then the system will learn. The system can remove the errors, remove the noise, or remove everything that you can see. This is not a good test or a bad test, or it can say just it can count the sperm test, even if you take this picture in a different light. So when we look at this picture, so we can just count the concentration of the light on the sperm test, and we can say just a 5 million, 2.5 million, or 1.5 million sperm tests. But the machine learning can discriminate even the 1 or 3 or 500 sperms. It can discriminate by comparing the human. So we reached the validation of the just by this little lateral flow based technique. So the validity of 0.62 million to 60 million sperm in 1 milliliter by using machine learning techniques. So the machine learning technique can just isolate the small circle, and it is not important for the machine learning device the concentration of the color is a little bit left, right, or the above. It's not important. It can just learn different patterns, different samples, or it can count the viscosity of the sperm. Then it can give us the count of the sperms. Another technique that I can provide you, the deep learning based quantitative female test. Just I mentioned before, the lateral, it is deep learning tests, deep learning based systems are very useful, the lateral flow techniques. Where in the laboratory, we have been using some lateral flow techniques. Can you see here, there's a lateral flow on the left, and this lateral flow is just like we created as a biosensor technology. So what is the system doing? First of all, system can analyze by using those Aruco markers. These Aruco markers are navigators, and this system can analyze the lines. How we can do that? So in picture A, this is just a picture, and B, we are and the codes put some grayscale images, and C, mapping, and maybe you can see at the end, at the E picture, there are green lines. These green lines are counters that the machine can see the green lines and count its color concentration. But if you look at the figure B at the right side of the calibration curve, the black one is without machine learning. The system only counts the colors, but it is not useful for the detection of anti-Mullerian hormone concentration. But if the machine can discriminate the specific signal, which is the line on the F picture, so it can give you a very perfect calibration curve, even if you are using a lateral flow techniques. So the deep learning method can do that. On the left, we cannot see the difference. We cannot see the difference by our eye, the concentration, but the system can decide even the 1 nanogram per milliliter ability to detect the concentration. The future of this test, we will turn this test into 4 different colored hormones, and we will add some ultrasound pictures by gynecologists, and all the system will turn into the fertility AI-based biosensor. Then the AI-based biosensor will give a female, then female, and it can say, yes, your fertility score is, for example, 8 out of 10, and you are fertile, and you can have a baby. The machine will decide, instead of taking lots of blood and taking a couple of clinical experiments and examinations. So the smart fertility biosensor will decide just 1 drop of blood, and the machine will do that instead of us. Another study of ours that is also the deep learning technique. So the deep learning has ability to detect insulin in our blood. In the small circles on the left bottom, you can see different color accumulations in different zones of these circles. So if we just read the color concentration, or if we just can look at the color concentration of the biosensor, the calibration curve is really awful. And we cannot decide the concentration which is true or not. So when the machine learning and deep learning techniques come into the show, and it can say to us, yeah, you have different shapes and different colors and different color types, but there are some errors, and I can calculate, and I can give you a perfect calibration curve by using it. So this will be a HOMA-IR biosensor, and it also gives us the glucose concentration, and it is also a deep learning based technique that it will just give the person your HOMA-IR, I mean the insulin resistance is high or low. It can only decide by using the just little small colors. Well, the last 2 slides with the electrochemical techniques, then I would like to give you new generation DNA sensors, and then how we can perform our small AIs in our laboratory. So detection of DNA in the blood is very powerful technique. So we called it like liquid biopsy. The liquid biopsy we can detect circulating tumor DNAs to analyze the tumor in the very early stages. So let's look at this electrochemical technique. This is just like a chronoamperometric technique, which can detect electrons in time. So it can detect electrons in time, but it has a ability to collect 30,000 points in 180 seconds. So we can see, and in the A, there's nothing. We can just spikes, high and low. And in the middle of this slide, you can see lots of words, lots of codes. I mean, there are 8 pages code that discriminate in the blood and it can analyze the exon 9 mutation in the breast cancer. So this is the single entity electrochemistry. Single entity can detect only one entity, only one DNA when it touches to the electrode. Let's follow the B and C, and our eye cannot see any difference by looking for this exon 9 mutation, but the right corner of the top, we can see red lines. This is a specific pattern of exon 9 mutation. This is a data analysis. Any electrochemist can analyze this data in 30 minutes, but when you write those codes, whenever you sit on your table and press the run button, it can give you the results. Yes, if there's a mutation, or if there's a cancer, or there is another genetical illness, it can give you in 2 seconds that you have a mutation or something. So the combination of lots of mutations, lots of circulating tumor DNAs in the blood, then it will say, yes, you have breast cancer, or you have uterine cancer, or you have another cancer. It can say at the end of the project. So we want to publish in 2 years as a DNA-based biosensor. So the last one that I would like to tell you is a deep learning technique, another technique that neural networks can discriminate the different viruses in different methods. We have been using the same method. So various viruses have different shapes and different electrical properties, or different molecular weights. So how we can describe that? And if they touch to electrodes, just as mentioned before, the single entity electrochemistry, so it will give us a signal. But which signal is which virus? First of all, we can integrate the machine that this virus pattern is, for example, dengue virus, or West Nile virus, or Zika virus. So these patterns can be integrated with the neural networks, and the neural network can decide, yes, this is a Zika virus. So we have been thinking this multiple virus biosensor is an early detection and early detection by using this mosquito-borne viruses. So the neural network will decide instead of us to as an early warning. So what is the at the end? The biosensor can detect by using its biochemical reaction any molecule, but it will give you a signal. Then the signal will be decided by scientists. And the scientists with lots of data, it's very time consuming, and it's very hard to diagnose any medical application. So if we add AI or machine learning or deep learning or neural networks to our biosensor data analysis system, these biosensors can learn, and the artificial intelligence can improve itself. So the biosensor technology can improve itself. We used to use actually Excel before to analyze the data. Now we are writing half of a page codes, and half of page can give us the calibration curve, LODs, LOQs, and if also the matrix effect, and it can give you everything, and it can decide instead of us. Well, my presentation is all, and thank you for your attention. And the chair, the word is yours.
Thank you, dear Dr. Onur, and for this futuristic speech. Okay, now let's start the Q&A section. We have many questions on the box. Now, for the first question for Dr. Deniz İlhan Topçu. Yes, thank you for the interesting presentations. I just wonder, as all intelligence systems need data to learn, where will these data come from? How is avoided that they are biased? Many clinical studies in the past were performed mainly with white men, for example, and how the AI evaluate the quality of the data used for the learning. Furthermore, if the sensors use data from clouds or other open access source to learn, these will be provided by the different instruments. This would assume that the results from the different instruments and different systems are comparable, which is not the case for many clinical markers. I think this is all about the biased data.
Actually, this is a very great question, and maybe the most important problem related to AI and machine learning is the obtaining correct data set. Bias is a big problem because, as you mentioned, Whiteman example is a great because there are different applications for detecting face, but these are or detecting some melanoma skin lesions, but they are generally trained in white skin, so they cannot be generalized for other populations. So to solve this problem, actually, I didn't have enough time to share this problem, but it is a very common problem in healthcare setting, and I think it is not different for biosensor perspective. To overcome this issue, we must include diverse data sets, which should include all kind of populations. And actually, because of this problem, the generalization is not always possible using AI and ML tools. And if you look at the actual applications of these tools related to clinical chemistry, they are really limited. For example, compared to radiology, because they are processing image. So the answer, in short, we should include all data, possible data, but I know it is not easy. And related to the second part of the question, as a clinical laboratory specialist, I know that the harmonization is very important problem among different analyzers. So um, without harmonization, it will be very difficult to train these or generalize these models. So very vigorous external validation is very, very important for testing these models. Otherwise, they will be biased, and we this is a very real and serious problem for us.
Yeah, yeah, yeah. Already some data are biased, especially in hospital setting. So another question, we have another question for you, dear Dr. Dennis. Thanks for an interesting review of the development of biosensor technologies. What about the degree of standardization of data interfaces between the different devices and common hospital and laboratory information systems?
Again, this is a very nice question, but I think we are lucky now compared to previous years, because now the standards between analyzers and the laboratory information systems or hospital information systems are very standardized now. For example, HL7 protocol is widely used, and generally vendors follows these protocols when integrating their devices with hospitals or laboratories. And there is also some legacy protocol, ASTM, which uses our older serial communication. So if vendors follow these protocols, generally they can be integrated in hospital and laboratory setting. For example, for now, point of care test devices, for example, glucometers in our hospital, is actually maintained centrally. All results obtained from glucometers also transferred into LAS system. All QC results are transferred into LAS system, so we can centrally evaluate the patient results or QC results.
Yes. Also, your response also answered the first question. Can glucometer results be interfaced with LIS? Yes, it is correct. Now, another question for Dr. Onur Uygun. I would like to know, if we don't have the data, is it fine to rely on the synthesized data for training the model? Do you have any tools or example for data synthesis?
Yeah, that's a good question. Firstly, we start with the data. Okay. For example, let's talk about the chronoamperometry or electrochemical impedance spectroscopy. It has own its shape. So we need to tell the Python coding that import the data processing, first of all. Then we will add, for example, electrochemical impedance spectroscopy. It has its own semicircular shape and the linear shape. So we will decide synthesized data, and we can program that device. Then we can control its electrochemical circuit model. And the circuit model is okay. Then the system can work with the new generation, new generated data by experimenting. But the synthesized data will be very perfect to analyze. But the system needs more laboratory-based data to integrate itself to learn. Otherwise, we will be developing a biosensor, but we cannot discriminate the false positive signals, or how can I say, it cannot discriminate the noise and the signal. So you can produce your machine learning or deep learning codes by using synthesized data, or you need to add some laboratory-based data then, and you can synthesize the data. And you ask something that if I have tools, to example, for data synthesis. Well, I have no idea right now because my all data are laboratory-produced data, but maybe you can reach out to the papers that you can find on the internet so that you can use their data by combining your system, and maybe you can produce your data. Thank you.
Okay. Another question for you, dear Dr. Onur. Can we
Yes.
use AI or the technologies that we discussed not only for prognosis, but also for usage of controlling developments after surgeries, traumas, so that we would be able to detect abnormalities? Is
That's
it
a
clear?
nice question. Yeah. First of all, you need to put all the knowledge to those codes. So they are just basic codes. If you search on the Google, then you can say the Python codes, you will see lots of codes. You need to learn Python to write the codes. And if you have some surgical operations, or if you have some very specific data, so if you add your data to your programming, then your program can discriminate what you are looking for. And you can program that. The coding, actually, I would like to say something, and the coding depends on your imagination. So if you put your imagination, everything in your codes, so you can do anything that you can decide.
Yeah, normally.
Thank you.
Okay. And another question from the beginning. Yes. AI needs a powerful computers. It means money. So if we want to produce a cheap sensors, there is a way to use AI and apply it in cheap sensors without the need of expensive computers. Maybe this question for Dr.
I
Ebru.
can answer that.
Okay, no problem. Okay, go ahead.
So all the presentation, all the techniques, all the image processings we carry out in Windows-based, very simple desktops. We can do that. We don't need very large, because we don't have a very large data. But if you are using next generation sequencing, because the next generation sequencings have around one sequencing is 120 gigabytes. So it needs to analyze this data. You need a very powerful computer. But if you are using electrochemical techniques, so it's our one chronoamperometry. is around 1 megabyte data. So you don't need any very powerful computer.
Mm-hmm. Yeah.
May
So
I add something to this question?
yes,
Actually,
please.
the CPU or GPU hungry part is the training of the model. If you, after obtaining the model, you can generally uh, apply that very simple computers. For example, there are some applications using some Arduinos or ESP devices, using some Python code. You can actually run the trained model. The training part is the GPU hungry part. After the deployment of the model, you can use much more simpler computers.
Yeah. And another question, maybe a long question. First question in the same from the same person. What is the primary necessity of intelligent biosensors in clinical decision support systems in healthcare settings? For CDS, intelligent biosensors, primary necessity. Maybe it will be about integration.
Actually, I have the last slide that I have in my presentation gives these necessities. It means that for the rural conditions, rural areas, and the other parts, and which we can't reach any hospital and etc., the necessity will become for the to get a real integrated biosensor which gives the result to the doctor or a hospital and come back to ourselves. So I think this is the question's answer, but I am not sure.
Yes. So second part of this question, what are the most critical components at the center of discussion for the future of AI biosensors technology? What is the most critical components? Maybe computer, maybe...
No, it's not the computer. It's the biosensor design actually. Because if you can manage to design a complete biosensor which can integrate AI, so you can manage to finish all the structures of an intelligent biosensor. The computer, the programs, and machine learning, etc., is just the processing. But on the other hand, we need a huge data. And I mean, we need a comparison data, not only the data coming from biosensor, but also coming from hospitals, automatized devices, and etc. We need to compare all of them, and we can via this way we can reach the final solution.
Yeah. And rest of this question, I think you answered. Now, next question. What are the main types of biosensors?
I didn't understood.
What are the main types, major types of biosensors? What what kind of biosensor? What sort of biosensor? For example, lateral flow or so.
Yes, I understand, but it depends on the transducer actually. Yes, there are some different types of biosensor related with the transducer, related with the techniques, related with the procedures, etc. There are a lot of, I mean, plenty. So it's a very general question. I don't know how to explain it. Maybe Dr. Uygun can explain more detailed.
Yeah. Yes.
Okay, if you wish, I can say something that about.
Yes, please.
The type mean, so there are three major types of the biosensor. The reaction that you are looking for first of all, if you would like to detect a protein or DNA or something, first you need to look into the target molecule should be electroactive or non-electroactive, or it can give you an optical signal or non-optical signal. Then you can decide the biosensor technique. So if it is an electrochemically active molecule such as glucose or vitamin C or vitamin D or any molecule, so you can just look into the unparametric techniques. This is the one type of the biosensor, catalytic type of the biosensor. If you have an interaction with the two biomolecules, for example, receptor, antigen and antibody, or receptor and the ligand, or DNA, or DNA or RNA biosensor. So you need to look into the non-electroactive techniques such as electrochemical impedance spectroscopy. So the types can be changed or can be altered or can be variable, but the main thing that you should know that the target molecules properties especially.
Yeah.
Thank you.
Okay. And it's about biosensors. What factors affect the sensitivity and specificity of a biosensors? For a biosensors sensitivity and specificity.
Yes. First of all, I can say the matrix, sample matrix, because you need to decide your biosensor type according to your analytes in a huge matrix, type of matrix actually. Then combination of the transducer and the other parts of the biosensor, biocomponents, etc. I wish we showed the biosensor design, how to use and have the components of the biosensor design. Then I can explain more clearly. But here, the sensitivity is related to biosensor properties. I mean, this is when you want to check the limit of detection in biosensors, you need to make optimization of all of the properties of the biosensor. This means you have to combine all of the properties and you have to in details of the biosensor. I don't know. I know I gave the answers in generally because this is a very huge deep learning in here. So maybe again, Dr. Onur will give the answer.
Okay, then if we talk about simple answer, so there is no specificity in the biosensor technology. We called it selectivity. So we call the selectivity of the biosensor. Specificity is such a different term for the biosensor technology. So the selectivity is related to the interaction with the analyte and the biorecognition receptor. So the biorecognition receptor, if it is very specific to target molecule, that your biosensor will be very selective. For example, antigen and antibody. But if you are using an enzyme and this enzyme can transform in two different substrates, then your biosensor selectivity is low. And sensitivity is based on the transducer. Transducer has a duty to collect all the electrochemical or optical signals and transduct to the computer. So if your transducer is a very sensitive to the signal, so your sensitivity is high. So you can increase your sensitivity by using nanoparticles, nanomaterials, or new generation devices. So I can give you answer like that.
Okay.
Yes. I just want to add something. As I gave in my presentation, in generations for electrochemical biosensors. by adding some mediators, particles and etc., and by improving the generations, we also improve the selectivity and sensitivity of the biosensor. So as Dr. Uygun tell about the specificity, it's a little bit more complicated when you use a biocomponent like antibody, enzyme, or some different aptamers and etc. You can decrease or increase. It depends on your features, actually. Sometimes you don't need to decrease the limit of detection too much in analytical consideration. So maybe you need some linearity between some concentration. It will be enough for you. You don't need to consider the detection limits too much for biosensors. Depends on your analytes and where you are going to use. Please also think about like this too. Thank you.
Okay, now last question. Also, other question will be replied by email. Sorry for the guests. And also, so which languages are generally used for AI? Can we use Arduino, for example? Maybe it's about coding.
Not for the model development. You cannot use Arduino, but generally machine learning is done with Python because lots of open libraries, TensorFlow, PyTorch is available on Python platform. So I think Dr. Uygun also have a comment about this thing, but before for my viewpoint and my experience, Python is the best solution to go.
Yeah, obviously. Okay. Last speech, dear speakers.
Well, do you want me to give you about the comments on Arduino or?
Yes,
No, that's enough.
about. But after you
Well,
can add some contribution
okay.
as last speech.
Okay. Well, Arduino is a device that can turn the analog signal of the biosensor turn into a digital signal. This is not about the AI deep learning technique. It is then you are programming a device such as a glucometer. Then you are saying that device detect those signals and measure the electrons and turn it to bit signals as a concentration. This is very far from the Python coding. Python coding is data processing. You obtain a data as an Excel file or another file, then this can turn this data for a very, how can I say, very meaningful data. So these are very different things. And I would like to thank the whole of the IFCC and all my colleagues to explain the AI-based systems. And thank you for all. And anyone who can reach me via email, I can answer their questions, or I can collaborate, or I can comment on their experiments. Thank you very much.
Thank you. Okay, now it's closing, and thank you for attending to this webinar, and thank you, Dr. Saatçi, Dr. Topçu, and Dr. Uygun for your interesting presentations that provided such valuable information on the topic we discussed. And of course, thanks to the IFCC for offering this tool for the e-learning. Please remember that if there are unanswered questions, they will be replied by email to those who posed the question that mentioned Dr. Uygun. And the certificate of participation will be provided at the end of this webinar after a few questions. At the end of the question, please click the Show My Scores at the end of the page and get your certificate, please. And last, the on-demand content of this webinar will be available in short, and you will be informed via email. There will be soon other IFCC free webinars, and they will be announced via IFCC communication channels, email, website, and IFCC social media. Thank you, and goodbye, dear guests and dear speakers. Bye.
Bye.